Chapter 18, Solid-State Technology and Programmable Controllers. The Programmable Logic Controller, PLC, typifies one of the most common and somewhat complex electronic systems. A PLC contains many solid-state components such as microchips, sensors, and switches, and thus can be used for many applications. Proper troubleshooting procedures must be followed when troubleshooting a PLC system or subsystem. Objectives: explain programmable logic controllers, PLCs. Describe areas of PLC applications. List and describe the PLC sections. Describe interfacing circuits. Explain the troubleshooting of PLC systems. Programmable logic controllers. A programmable logic controller, PLC, is a solid-state control device that is programmed and reprogrammed to automatically control processes or machines. Programmable memory is used to store instructions by implementing functions such as logic sequencing, timing, and counting for process and machine control. The PLC was first developed in response to the needs of the automotive industry. Annual model changes required constant modifications of production equipment controlled by relay circuitry. In some cases, entire control panels had to be scrapped, and new ones designed and built with new components. This resulted in increased production costs. The automotive industry was looking for equipment that could reduce the changeover costs associated with model changes. In addition, the equipment had to operate in harsh factory environments of dirty air, vibration, electrical noise, and wide temperature and humidity ranges. To meet this need, the PLC, a rugged computer-like control, was constructed. The PLC could easily accommodate constant circuit changes using a keyboard to introduce new operation instructions. In 1968, the first PLC was delivered to General Motors, GM, in Detroit by Modican. PLCs must be installed in an enclosure or cabinet. All cables connected to a PLC must remain in the enclosure or be protected by conduit or other means. The first PLCs were large and costly. They were an UTLI used in large systems with 100 or more relays. Today, PLCs are considerably smaller. PLCs are manufactured from small sizes that control a few input and output terminals, devices, and components, to large sizes that control thousands of input and output terminals. PLC system programming can be viewed using software with integrated programming devices, handheld programming devices, operator interface panels, and personal computers. See Figure 18:1. Integrated programming devices. An integrated programming device is a device that consists of a small LCD and a small keypad or set of buttons that are part of a PLC. Integrated programming devices are typically found on small-size PLCs. A PLC program is entered into the PLC using the keypad and viewed on the LCD display. Using integrated programming devices is a convenient way to access PLC programs without additional hardware. However, small LCDs provide only limited viewing, and making programming changes with integrated keypads is typically time-consuming. Handheld programming devices. A handheld programming device is a separate keypad device that is not an integral part of a PLC. A handheld programming device is about the same size as a personal digital assistant, PDA, but with a larger display and keypad, and an integrated programming device. A handheld programming device connects to a PLC with a cable and connector. As with integrated programming devices, handheld programming devices are typically used with small PLCs. Handheld programming devices are used to enter, copy, display, store, and transfer PLC programs. The ability to copy, store, and transfer a PLC program allows a handheld programming device to be used with multiple PLCs having the same type of programming. Although the display and keypad are larger than that of an integrated programming device, viewing and editing are still limited with handheld programming devices. Operator interface panels. An operator interface panel, also known as a human-machine interface, HMI, is a display panel that is connected to a PLC by a communication cable. An operator interface panel uses text, graphics, or a combination of text and graphics to provide real-time representation of a process or application. Buttons on an operator interface panel provide access to different screens and or control functionality of the process depicted. Operator interface panels come in a variety of sizes, with either monochrome or color displays. Although PLCs cannot be directly programmed from operator interface panels, the parameters of certain instructions can be adjusted, such as counter and timer preset values. PLC applications. For typical areas in which PLCs are used include medical, manufacturing, mining, and building automation. See Figure 18:2. Industries requiring high-speed monitoring and control of processes depend on the use of PLCs. Beverage and food packaging industries use PLCs for conveyor belt control, container positioning, sensing, file level detection, and counting products. PLCs are used in highway traffic signals and parking lots for timing and counting functions. PLCs are used in pipelines and water and wastewater facilities for flow detection and regulation. Airport baggage handling is also accomplished with PLC usage. The future of programmable controllers relies not only on the continuation of new product developments, but also on the integration of PLCs with other control and factory management equipment. PLCs are being incorporated through networks into computer-integrated manufacturing (CIM) systems. The power and resources of PLCs are being combined with numerical controls, robots, CAD/CAM systems, personal computers, management information systems, and computer-based systems. Programmable controllers will continue to play a substantial role in future control applications. PLC sections. Although PLC sections are found in various shapes, sizes, and forms, they are physically constructed as individual fixed packages or modular designs, which allow greater design flexibility. See Figure 18-3. In many cases, programming is done offline, and the programming device is not shown. All PLCs have 5 basic sections. A PLC consists of a processor, input, output, programming, and power supply section. The processor is used to control the systems. The input section is used to receive information from push buttons, limit switches, sensors, etc. The output section is used to control magnetic starter coils, lights, solenoids, etc. The programming section is used to allow technicians to view current programming and future edits. Using a schematic diagram of a modular programmable logic system is the easiest way to show how the basic sections of a PLC relate to one another. See Figure 18-4. The programs used in manufacturing parts and equipment, and in processing goods and other consumables are stored in and retrieved from memory, as required. Sections of the PLC are interconnected and work together to allow the PLC to accept inputs from a variety of sensors, make logical decisions as programmed, and control outputs such as motor starters, solenoids, valves, and drives. All PLC wiring should be installed in a neat and professional manner. Figure 18-4. A schematic diagram and pictorial are used to show how PLC sections are interconnected. Figure 18-5. The processor section organizes all control activity by receiving inputs, performing logical decisions according to the program, and controlling outputs. Figure 18-6. The processor receives signals from input devices, compares the signals with information in the PLC program, and sends signals through the output section to turn output components on and off. E18-5. Processor section. A processor section is the section of a PLC that organizes all control activity by receiving inputs, performing logical decisions according to the program, and controlling outputs. See Figure 18-5. The processor section is the brain of the PLC. The processor section evaluates all input signals and levels. This data is compared to the memory in the PLC, which contains the logic of how the inputs are interconnected in the circuit. The interconnections are programmed into the processor by the programming section. The processor section controls the outputs based on the input conditions and the program. The processor continuously examines the status of the inputs and outputs and updates them according to the program. See Figure 18-6. Figure 18-6. The processor receives signals from input devices, compares the signals with information in the PLC program, and sends signals through the output section to turn output components on and off. PLC memory. Memory is an electronic storage device for digital data used in computers. Memory consists of a solid-state microchip onto which data is stored at specific addresses inside the processor section. The processor of a PLC contains memory in which the PLC program and related data are stored. The two areas in the memory of a PLC are program files and data. Program files are files that contain the user-developed control program, PLC program. A data file is the section of PLC memory that contains the status of inputs and outputs, timer preset values, counter preset values, and other program instruction values. See Figure 18-7. Figure 18-7. PLC memory includes RAM and EEPROM. Memory can be volatile or non-volatile. In the event of a power failure, volatile memory loses stored data, while non-volatile memory remains intact. Most PLCs contain both types of memory. Random access memory, RAM, is a type of computer memory that is lost when power is lost. RAM is used by PLCs to store program files and data. A PLC program is run while stored in RAM memory. A battery is used to provide backup power so that data will not be lost when normal power is turned off or lost. Erasable programmable read-only memory, EEPROM, is a type of computer memory that can be programmed and erased, enabling it to be reused. Erasure is accomplished using ultraviolet UV light that shines through a quartz erasing window in the EEPROM package. Electronically erasable programmable read-only memory (EEPROM) is similar to EEPROM, but the erasure is accomplished using an electric field instead of a UV light source. This eliminates the need for a window. EEPROM is a type of memory that is retained when power is lost. EEPROM is used in PLCs to provide a backup for the RAM memory. A copy of the PLC RAM program is stored in EEPROM memory. Typically, data is transferred from RAM to EEPROM upon power loss. At power-up, data, including the PLC program, is transferred from EEPROM to RAM. The EEPROM can be an integral part of a PLC or a separate unit that plugs into a PLC socket. Most PLCs use a type of solid-state EEPROM chip as a memory module. EEPROM are configured using an EEPROM program that provides voltage at specified levels depending on the type of EEPROM used. Solid-state motor starters produce minimal electronic noise. This is beneficial if PLCs, computers, microprocessor-based equipment, or other devices that may be affected by electronic noise are located nearby. PLC input section. An input section is the section of a PLC that receives signals from input devices and sends the signals to a CPU. Push buttons, limit switches, and proximity switches are common input devices. See Figure 18-8. Each input device is connected to a specific screw terminal that corresponds to a specific location, address, in the memory of the CPU. Typically, each PLC input screw terminal has an LED to indicate when an input device is closed, sending signal and voltage is present at the input terminal. Figure 18-8. Input devices, such as push buttons, limit switches, and proximity switches, are connected to the input modules of PLCs. PLC input section. Internal circuitry. Input devices typically operate at voltages higher than the voltage used by the CPU, 5 volt. Optical isolation is used by PLCs to convert high-voltage input signals to a voltage level the CPU can use. Inside AC power PLCs, AC input signals are converted to DC by a rectifier, and the DC signal turns on an LED. See Figure 18-9. The light from the LED is detected by a phototransistor, and the phototransistor sends a signal to the CPU. In most cases, the phototransistor and the CPU operate at the same voltage level. Figure 18-9. The input section of a PLC is the section that receives signals from input devices and sends the signals through its internal circuitry to the CPU. The input section can be either located on the PLC, onboard, or part of an expansion module. An onboard input terminal is a permanent part of the PLC package. Expansion modules are removable units. Various input module types allow analog and digital input devices to send information to the PLC. An analog input device sends a continuous IC hanging variable signal to the PLC. Temperature, pressure, flow, and level sensors are common analog input devices for a PLC controlled system. On/off switches such as push buttons, limit switches, and toggle switches are common digital input devices. A digital input device is a device that is either on or off, open or closed. PLC input voltage ratings. All PLC input devices, such as push buttons, level switches, and proximity switches, are connected to input terminals. The input device circuit must be powered by a specified voltage or voltage range. PLC input terminals are available with DC, AC, or DC/AC ratings. A low-voltage rated input terminal, 12 VDC or 24 VDC, is the most common and preferred type of PLC input terminal. Lower voltages are safer and provide for an easier installation because low voltages do not require input wires to be run in conduit. Many PLCs provide 12 VDC or 24 VDC output power terminals that can also be used to power input terminals. See Figure 18-10. AC-rated PLC input terminals cannot be powered by DC power. Likewise, DC-rated PLC input terminals cannot be powered by AC power. When inspecting a de-energized PLC, electrostatic discharge from the human body can damage integrated circuits and semiconductors of the PLC when internal components are touched. PLC input current ratings. PLCs are designed for DC or AC input voltages. When using switches with mechanical contacts, such as standard push buttons or mechanical limit switches, the switches can be connected to either DC input terminals or AC input terminals. A DC-rated solid-state input switch should only be connected to the input terminal of a D-rated PLC. An AC-rated solid-state input device should only be connected to the input terminal of an AC-rated PLC. The amount of current in the input circuit of a PLC is low, because the internal circuitry of the PLC input section is the load of the input circuit. The internal circuitry only requires a few milliamperes mA of electron flow to activate. A typical PLC input section only draws about 5 mA to 20 mA of current. See Figure 18-11. However, low current inputs of a PLC are capable of controlling high current outputs with the appropriate interfacing circuitry. Figure 18-10. Low voltage rated input terminals, 12 VDC or 24 VDC, are the most common and preferred PLC input terminals. Figure 18-11. The internal circuitry of a PLC only requires a few milliamperes of electron flow to be activated. DC input switching. DC power is commonly used with PLC input circuits. The advantage of using DC is that a DC supply is kept to a low level, typically 12 VDC or 24 VDC, for safety. Also, most photoelectric and proximity sensors typically use transistors as the switching element and are rated to operate in a range between 10 VDC and 30 VDC. The two types of DC input switches are 2-wire and 3-wire input switches. A 2-wire input switch circuit uses solid-state, photoelectric and proximity switches or mechanical limit switches for switching. A 3-wire input switch circuit uses solid-state switches for switching. See Figure 18-12. A 3-wire input switch circuit typically uses an NPN or PNP transistor as the switching device. For most applications, the exact transistor used does not matter as long as the switch is properly connected into the input circuit of the PLC. However, NPN transistor switches are far more common than PNP transistor switches. PLC input terminals are rated as current sink, current source, or current sink/source. PLC input terminals rated as current sink/source can be used with NPN or PNP solid-state switching devices. When using an NPN transistor type input device, the load PLC input section is connected between the positive terminal of the supply voltage and the output terminal collector of the switch or sensor. When a switch, such as a photoelectric or proximity sensor, detects a target, electrons flow through the transistor switch and the PLC input terminal is energized. See Figure 18-13. Switching devices that use NPN transistors as the switching element are called current sink, negative switching, or NPN devices. A sink is the negative power supply terminal of a DC-powered PLC. Sinks use conventional flow-through NPN transistors. A current sinking switch sinks current from the load when using a PNP transistor type input device. The load PLC input section is connected between the negative terminal of the supply voltage and the output terminal collector of the switch or sensor. When the switch detects a target, electrons flow through the transistor, and the PLC input terminal is energized. See Figure 18-14. PLC DC input devices can be configured as sinking or sourcing, depending on how the DC-COM terminal is wired into the input circuit device. Switching devices that use PNP transistors as the switching element are called current source, positive switching, or PNP devices. A source is the positive terminal of a DC-powered PLC. Sources use electron current flow through PNP transistors. A current sourcing switch sources current to the load. Figure 18-14. Switching devices that use PNP transistors as switching elements are called current sourcing, positive switching, or PNP devices. Troubleshooting input modules. It is very important to choose the proper testing equipment when working on any electronic system. Some types of testing equipment can actually cause failures in the system they are testing. One example is a vibrating voltage tester, WIGI. It must never be used to measure the voltage level at any input to a PLC. A vibrating voltage tester contains a solenoid. When the test leads of a vibrating voltage tester are removed, the collapsing field of the solenoid can damage the solid-state components of the input module. Signals and information sent to a PLC using input devices are connected to the input module of the PLC. The controller cannot function if the proper information from the input device or input module is not communicated. See Figure 18-15. When troubleshooting, it is important to start with the input section and see if it is operating properly, since there could be multiple input devices feeding the input module. To troubleshoot the input module of a PLC, apply the following procedure. 1. Measure the supply voltage at the input module or card to ensure that the required power is supplied to the input device. Voltage can vary as required. Test the main power supply of the controller when there is no power. 2. Measure the voltage from the control switch. Connect the DMM directly to the same terminal screw to which the input device is connected. The DMM should read the supply voltage when the control switch is closed. The DMM should read the full supply voltage when the control device uses mechanical contacts. The DMM should read nearly the full supply voltage when the control device is solid state. Full supply voltage is not read because 0.5 volt to 6 volt is dropped across the solid state control device. The DMM should read 0 or little voltage when the control switch is open. 3. Monitor the status indicators on the input module. The status indicators should illuminate when the DMM indicates the presence of supply voltage. 4. Monitor the input device symbol on the programming terminal monitor. The symbol should be highlighted when the DMM indicates the presence of supply voltage. Replace the control DEVIs if the control device does not deliver the proper voltage. Replace the input module if the control device delivers the correct voltage but the status indicator does not illuminate. Troubleshooting input devices. Input devices, such as push buttons, limit switches, pressure switches, and temperature switches, are connected to the input modules of a PLC. Input devices send information and data concerning circuit and process conditions to the controller. The processor receives the information from the input devices and executes the program. All input devices must operate correctly for the circuit to operate properly. See Figure 18 to 16. To troubleshoot the input device of a PLC, apply the following procedure. 1. Place the controller in the test or program mode. This step prevents the output devices from turning on unexpectedly and creating a hazard. Output devices will be turned on when the controller is placed in the run mode. 2. Monitor the input devices. The input devices can be monitored using the input status indicators on each input module, the programming terminal monitor, or the data file. The data file consists of data values, inputs, timers, counters, and outputs that are displayed on the monitor to give additional information regarding what should be taking place in the control process. This information often looks like truth tables. 3. Manually operate each input starting with the first input. Never reach into a machine when manually operating an input. Always use a wooden stick or other non-conductive device. The input status indicator located on the input module will illuminate, and the input symbol will be highlighted in the control circuit on the monitor screen when a normally open input device is closed. The input status indicator located on the input module should turn off. The input symbol should no longer be highlighted in the control circuit on the monitor screen when a normally closed input device is open. The next input device should be selected. Each input device should be tested until all inputs have been tested. PLC output sections. An output section is the section of a PLC designed to deliver the output voltage required to control alarms, lights, solenoids, and other loads. The output section receives low-power digital signals from the processor and converts them into high-power signals. These high-power signals can drive loads that can light, move, grip, rotate, extend, release, heat, and perform a multitude of other functions. Onboard outputs usually contain a fixed number of outputs that will define the limits of the PLC. For example, a small PLC may include only 8 outputs. Therefore, the PLC may only control 8 devices unless an expansion module is added to the system. Figure 18 to 16. All input devices, such as push buttons, limit switches, pressure switches, and temperature switches, must operate correctly for the circuit to operate properly. Pilot lights, control relays, motor starters, and solenoids are typical components controlled by PLCs. See Figure 18 to 17. Each output component is connected to a specific screw terminal of the output section that corresponds to a specific location in the memory of the CPU. Each PLC output screw terminal has an LED to indicate when voltage to energize an output component is present at the terminal. PLC output section internal circuitry. Output components typically operate at a voltage that is higher than the operating voltage of the CPU, 5 volt. Optical isolation is used to convert low-level voltage signals from the CPU to a voltage that an output component can use. Inside the PLC, low-level voltage signals are used to turn on an LED. The light from the LED is detected by a phototransistor, which turns on a triac. Triacs are used to turn output components on and off. The CPU and the LED of the phototransistor operate at the same voltage level. See Figure 18 to 18. Solid-state outputs normally have fusing on the module to protect the triac or transistor from moderate overloads. If the output does not have internal fuses, then fuses should be installed externally, normally at the terminal block, during the initial installation. When adding fuses to an output circuit, manufacturer recommendations for the particular module should be followed. Only a properly rated fuse will ensure that the fuse will open quickly in an overload condition to avoid overheating of the output switching device. Figure 18 to 17. Output components, such as pilot lights, control relays, motor starters, and solenoids, are connected to the output modules of a PLC. Figure 18 to 18. The output section of a PLC is the section that receives signals from the CPU through internal circuitry and sends the signals through to the output components. PLC output voltage ratings. All PLCs have output components such as lamps, solenoids, and motor starters connected to output terminals. The output terminals of a PLC are powered by a specific voltage or voltage range. The type of voltage, AC or DC, and voltage level, 12 volt, 24 volt, or 115 volt, used for a PLC are based on the loads controlled by the PLC. Loads that require more power typically have higher voltage ratings because power, P, is equal to voltage, E, multiplied by current, I. The higher the voltage rating for a load, the lower the current rating for any given power rating. The output terminal switches of a PLC are either solid-state switches or mechanical contact switches. See Figure 18 to 19. The advantage of a mechanical contact output terminal is that a mechanical contact can switch either AC or DC loads. An AC solid-state output terminal of a PLC can only switch AC loads, and a DC solid-state output terminal can only switch DC loads. Solid-state output switches of PLCs include triacs for switching AC circuits and transistors and SCRs for switching DC circuits. Figure 18 to 19. The output sections of PLCs use transistors, triacs, and solid-state switches, or mechanical contact switches. Over travel, interlocks, and stop push-button safety circuits of a machine must be hardwired in series directly to the master control relay, which allows the relay to be de-energized. PLC output current ratings. PLC output components connected to the output section of a PLC determine the amount of current a PLC must carry. The amount of current drawn by an output component can vary from a few milliamps, small indicating lamps, to several amps, solenoids, higher wattage lamps, small motors, and large motor starters, to hundreds of amps, large three-phase motors, and three-phase heating elements. The current rating of PLC output circuitry is listed for the amount of current the internal switches can safely handle when the load is first turned on, make current rating, when the load is operating, continuous current rating, and when the load is turned off, break current rating. When AC loads are running, the break current rating will always be much lower than the make or continuous current ratings. This is because when an AC circuit is turned off, a large damaging current will try to arc across any switch that is beginning to open. With AC circuits, the arc dissipates somewhat because AC current is always fluctuating between 0 and peak current. However, in a DC circuit, there is no fluctuation, making switching DC circuits more damaging. Because of the possible damage, a PLC output relay contact or output switch will have a much lower DC rating than AC rating for the same output switch. Troubleshooting output modules. A PLC turns on and off the output devices, loads, in the circuit according to the process or work it was designed to control. The output devices are connected to the output module of the PLC. No work is performed in the circuit when the output module or the output devices are not operating correctly. The problem may lie in the output module, output device, or controller when an output device does not operate. See Figure 18 to 20. To troubleshoot the output module with the PLC, apply the following procedure. Measure the supply voltage at the output module to ensure that there is power supplied to the output devices. Test the main power supply of the controller for voltage supplied to the output devices. Testing for voltage can be done in the run mode but would be easier when using the force mode. 2. Measure the voltage available from the output module. Connect the DMM directly to the same terminal screw to which the output device is connected. The DMM should read the supply voltage when the program energizes the output device. The DMM should read full supply voltage when the output module uses mechanical contacts. The DMM should read almost full supply voltage when the output module uses a solid-state switch. Full voltage is not read across solid-state switches because 0.5 volt to 6 volt is dropped across the solid-state switch. The DMM should read 0 or little voltage when the program de-energizes the output device. 3. Monitor the status indicators on the output module. The status indicators should be energized when the DMM indicates the presence of the supply voltage. 4. Monitor the output device symbol on the programming terminal monitor. The output device symbol should be highlighted when the DMM indicates the presence of supply voltage. Replace the output module when the output module does not deliver the specified voltage. When the output module does deliver the correct voltage but the output device does not operate, troubleshoot the output device. Troubleshooting output devices. As noted earlier, output devices, such as motor starters, solenoids, contactors, and lights, are connected to the output modules of a PLC. An output device performs the work required for an application. The processor energizes and de-energizes the output devices according to the programming entered. All output devices must operate properly for the circuit to operate properly. See Figure 18 to 21. To troubleshoot the output device of a PLC, apply the following procedure. 1. Place the controller in the test or program mode. Placing the controller in the test or program mode prevents the output devices from turning on. Output devices will be turned on when the controller is placed in the run mode. In some cases, it is more accurate to take measurements in the run mode when full load conditions are present. All safety issues must be addressed when testing in the run mode. 2. Monitor the output devices using the output status indicators located on each output module, the programming terminal monitor, or the data file. 3. Activate the input that controls the first output device. Check the program displayed on the monitor screen to determine which input activates which output device. Never reach into a machine to activate an input. Figure 18 to 20. When the output module is not operating properly, the output circuit does not operate properly. Figure 18 to 21. All output devices must operate properly for the output circuit to operate properly. The next output device should be selected and tested when the status indicator and associated bit status match. Each output device should be tested. Troubleshooting of input and output devices should occur when the status indicator and associated bit status do not match. PLC interfacing circuits. Once all loads, lamps, motors, or heating elements are identified, the exact types of control devices and output components required to make the circuit operate as designed are selected. Low-power output components are connected directly to the output terminals of the PLC as long as the output component voltage, current, and power ratings are less than the maximum rating of the PLC output module. An interface device is required when the power requirements of the load are higher than the ratings of the output module. A high power load is a load with a voltage and current rating greater than the voltage and current rating of the PLC output. The most common interface devices used to allow PLCs to control high power loads are relays, contactors, and motor starters. See Figure 18 to 22. Figure 18 to 22. Interfacing devices, such as SSRs, magnetic contactors, and magnetic motor starters, are connected to the output modules of a PLC. Relays. A control relay is a device that controls an electrical circuit by opening and closing contacts in another circuit. A solid-state relay, SSR, is a switching device that has no contacts and switches entirely by electronic means. In an SSR, the coil is replaced by an input circuit and the contacts are replaced with a solid-state switching component, transistor, SCR, or triac. Relays typically have low-power rated contacts and are used for switching low-power loads such as alarms, small solenoids, and very small, milliwatt motors. Low-power loads can be connected directly to a PLC as long as the load is less than the PLC output section rating. However, by using a relay between the load and the PLC, the circuit and system is better protected. The input circuit of an SSR is activated by applying a voltage to the circuit that is higher than the specified pickup voltage of the relay. Most SSRs have an input voltage range of 3 VDC to 32 VDC. The voltage range allows a single SSR to be used with most electronic circuits and PLC output modules. The switch circuit output of an SSR is controlled by the input signal. Most SSRs use thyristors for AC switching or SCRs for DC switching as the output switching components. Thyristors and SCRs, or gates, change from an off state, contacts open, to an on state, contacts closed, very quickly when the input is energized. The gate of an SSR is switched on when the relay receives the proper input signal. The type of relay used for an application depends on the life expectancy, electrical requirements, and cost of the application. SSRs can be rated for billions of operations. In applications that require thousands of switching operations a day, such as with flashing lights and high-speed production lines, SSRs are essential. Contactors. A contactor is a control device that uses a small control current to energize or de-energize the load connected to it. Contactors have high-power rated contacts and are used for switching high-power loads such as lamps, fluorescent and HID, heating elements, transformers, and small motors, less than quarter horsepower, that have built-in overload protection. Contactors are required between the PLC output section and high-power loads. Motor starters. A motor starter is an electrically operated switch that can turn a motor on and off and includes motor overload protection. Motor starters are used for switching most motors over quarter horsepower and all motors over 1 horsepower. Contactors and motor starters are available in sizes that switch loads ranging from a few amperes to several thousand amperes. Motor starters are required between the PLC output section and high-power loads. Troubleshooting PLC systems. PLC troubleshooting typically falls into one of two categories, software or hardware. A PLC software malfunction is a condition in which a PLC is properly installed and all inputs and outputs are working, but there is a problem with the PLC program. The PLC does not execute the programmed instructions necessary for the completion of the tasks assigned. PLC software problems. Technicians must be aware of the PLC software program for the type and model of PLC being serviced and how the electrical control system operates. PLC programs include symbols that represent series parallel and series parallel connected input devices and output components. An example of a PLC software error is two outputs, such as a motor and a light, which cannot be connected in series. See Figure 18 to 23. PLC hardware system problems. As previously indicated, troubleshooting is the systematic elimination of various parts of a system or process to locate a malfunction. A system is a combination of components, units, or modules that are connected to perform work or meet a specific need. A process is a sequence of operations that accomplish desired results. A malfunction is the failure of a system, piece of equipment, or part to operate properly. Since an electronic system controls the work performed by the electrical system of a machine or process, PLCs are one of the most logical places to start troubleshooting. See Figure 18 to 24. The advantages of starting at the PLC electrical system include the following. The input status lights, LEDs, of the PLC electronic input section or module provide a visual indication of which input devices are sending signals to the PLC, input status light on, and which switches are not sending signals, input status light off. The PLC input section or module provides a central location for checking all input device signals for proper electrical levels using test instruments. The output status lights, LEDs, of the PLC output section or module indicate which output components are energized, output status light on, and which output components are de-energized, output status light off. The PLC output section or module provides a central location for checking all output components, lamps, and solenoids, for proper signals or system output interfaces, heating/lighting contactors, or magnetic motor starters, for proper signal levels using test instruments. The operational status lights, LEDs, of a PLC provide a visual indication of when a PLC has power, when it is in the run mode, which inputs and outputs are being forced, when a CPU fault occurs, and when the backup battery is low. Laptops can be used to monitor a PLC by connecting the PLC to a laptop. In addition to monitoring the status of circuit input devices and output components, the timers, counters, and sequencers of a PLC can also be monitored. Once connected to a computer, input terminals can be forced on or off and output terminals can be forced on or off. The ability to force input devices and output components helps to isolate faulty equipment. Figure 18.23. When all PLC system hardware is functioning but the system is not operating correctly, the problem may be with the software. For example, the program or symbols may be incorrect, or the program may not be keyed correctly into the PLC. When troubleshooting a PLC, heavy, electronic, noise-generating equipment should not be located too close to the PLC. Unnecessary items should be kept away from any equipment in an enclosure. Leaving items, such as drawings, installation manuals, or other materials, on top of the CPU rack or other rack enclosures can obstruct airflow and create hotspots, which can cause system malfunction. If the electronic system enclosure is in an environment that exhibits vibration, a vibration detector should be installed. This way, the electronic system, PLC, can monitor high levels of vibration, which can lead to loose connections. Troubleshooting procedures based on knowledge and experience. Troubleshooting using knowledge and experience is a troubleshooting method used for finding a malfunction in a piece of equipment or process by applying information acquired from past malfunctions. In certain circumstances, troubleshooting using knowledge and experience is only partially effective because the primary malfunction is not corrected. For example, a fuse can blow, or a circuit breaker can't energize a part or all of a PLC control LED system. Records may indicate that changing the fuse or resetting the breaker allows the system to continue operation, but the reason for the blown fuse or tripped circuit breaker may not be known. See Figure 18.25. Troubleshooting using knowledge and experience is improved when the following conditions exist. Information about system components is gathered, and the operation of various primary systems are studied and understood. Communication with other individuals, supervisors, or operators familiar with the system is used to gain information about the work or process of the equipment or process with which the technician is working. Supervisors or operators familiar with the system may not know the electrical, fluid power, or mechanical reasons that a machine or process works, but may know about strange noises or any other unusual behavior that occurred before the malfunction. All service calls are documented for future reference. These documents include listings of all troubleshooting findings, information about system components is gathered, and the operation of various primary systems are studied and understood. Communication with other individuals, supervisors, or operators familiar with the system is used to gain information about the work or process of the equipment or process with which the technician is working. Supervisors or operators familiar with the system may not know the electrical, fluid power, or mechanical reasons that a machine or process works, but may know about strange noises or any other unusual behavior that occurred before the malfunction. All service calls are documented for future reference. These documents include listings of all troubleshooting findings and repairs as well as all components checked and found to be good when a malfunction is found and corrected. All suggestions that may help prevent the malfunction from recurring are noted for preventive maintenance. The technician knows how input devices and output components are monitored and or forced on and off, how the program can be displayed and printed, and how system changes can be programmed into a PLC, including who is authorized to make any modifications. The test instruments used and the measurements taken are documented for future use. For example, voltage measurements taken over time can indicate a power quality problem, such as transients, high voltage spikes, present on power lines. Figure 18.25. Troubleshooting using knowledge and experience is a troubleshooting method used for finding a malfunction in a piece of equipment or process by applying information acquired from past malfunctions. Troubleshooting using manufacturer flowcharts. Some PLC manufacturers include flowcharts with the PLCs to aid in troubleshooting. A flowchart is a diagram that shows a logical sequence of steps for a given set of conditions. Flowcharts help troubleshooters to follow logical paths when trying to solve problems. Symbols and interconnecting lines are reused in flowcharts to provide analytical direction to the troubleshooting process. See Figure 18.26. The symbol shapes used in flowcharts include ellipses, rectangles, diamonds, and arrows. An ellipse symbol is a symbol in the flowchart that indicates the beginning and end of a section of the chart. A rectangle symbol is a symbol in the flowchart that contains a set of instructions. A diamond symbol is a symbol in the flowchart that contains a question, worded so that the answer can be a yes or a no. An arrow symbol is a symbol in the flowchart that indicates the direction to follow through the rest of the chart based on the answers to the questions. Any change to the program of a PLC can dramatically change the operation of a process or machine. Figure 18-26. Flowcharts help troubleshooters to follow logical paths when trying to solve problems.